In a previous video, I talked about the slag color and how it was used to identify the gangue material in the ore or your concentrates. In part 10, I discussed and showed the calculations used for the required amount of silica and borax used to fuse the slag. Because the fusing of the gangue material forms part of the slag, I mentioned that in the next presentation, I would extend some additional techniques used to help identify the gangue material and the approximate quantity. In this presentation, presentation 11, I will be introducing the additional tools which should help in the identification as well as the approximate concentrations. I am Rob Boyko, Boyko Mineral Exploration, and welcome back. Vanning is not much more than a process of panning to gravimetrically separate the constituents making up the ore or concentrates. The technique is slightly different, however, it can be very useful in separating the flour gold in your concentrates. In reference to knowing what the gangue material is, vanning will give you some indication of what your contaminants may be, along with a guesstimate of their concentrations. In the lab, a pulverizer or a grinder is used to break the material down to roughly -100 mesh. Mortar and pestles are also used, but in the field, a dolly pot is more commonly used. These can be purchased and are relatively inexpensive, but most folks having the skills and tools will generally build theirs from scrap metal. As for the vanning equipment in the lab, the technicians will generally use a ceramic vanning plate. However, a ceramic dinner plate of the same shape can also be utilized for this purpose. There are special shovels that can be purchased, but an ordinary spade, as shown, works quite well. Most small-scale miners or prospectors will just use their metal gold pans. The intent is to try and determine what the percentage and type of minerals that would make up your slag in your ore concentrates. This is important when calculating the required flux material for your charge in order to achieve a slag that is readily fusible at furnace temperatures. Your flux constituents will vary between ore sample and ore concentrate. If your ore is basically the same, coming from the same source material, then knowing the constituents and concentrations within the sample, a single flux recipe can be developed. In large-scale enterprises, daily lab tests are conducted and the flux ingredients are accurately adjusted. But for the small-scaled operation, vanning will give you a starting point. That is a baseline for your flux recipes. In the next slide will be a good presentation of the procedure by F.L. Schmid. It's a vanning plaque tutorial.
I'm going to demonstrate the use of a vanning plaque that we use to separate minerals by specific gravity when we're running a processing test such as flotation. It's a valuable tool that you can use. You use this to separate the minerals, and then you can look at them under the microscope so that you can tell what you're doing when you're running the test. Taking approximately 100 milliliters of flotation slurry, which will give me approximately 50 grams of solid sample. The first thing you do is to wash off the slimes so that you can see what you're doing. Usually 2 or 3 washings are enough to remove the slimes so that you don't obscure minerals that you're trying to look at. Okay. So this is about the right amount of material on the vanning plaque. Like I say, it's approximately 50 grams. You use enough water to cover the sample so that you can fluidize it. This is about the right amount here. And then the key to the technique is you swirl the plaque with the sample in it to fluidize it, and at the same time that you're swirling, you hit the edge of the vanning plaque to bring the heavy minerals to one side. And the heavy minerals will travel towards the edge of the vanning plaque that your tapping motion is on. Okay. Remove the excess water. And what we have here is the heavy minerals. In this case, this is a sulfide sample, gold-bearing pyrite, is now separated from the gangue mineral, which is mostly quartz. You can now look at this material under the microscope and see if you've got good liberation, locking, or whatever other features you want to look at. There occasionally, if you're looking at a concentrate sample that has reagents added, you'll form a froth on top. And you can break this froth up by spraying it with a solution that's half gram per liter Cytec Aero Dry 100 or some similar surfactant.
As will be explained in an upcoming presentation, it is necessary to determine which class of ore you have and what you may have for contaminants. This is where some basic solutions chemistry is utilized. Any carbonate will react with hydrochloric acid. Placing a drop or two of diluted acid will result in fizzing actions, or effervescence as it's termed. However, with a dolomite specimen, which is basically a mix of calcium carbonate and magnesium carbonate, not much will result unless the dolomite is powderized. A streak plate can be used to obtain a substantial powder streak to which the acid can then be applied. It is then due to the small particle size that the dolomite will react. Heated hydrochloric acid will also react without powderization. Warming hydrochloric acid in the field is difficult. In regards to flux calculation, Class 1 and Class 3 ores or concentrates are treated the same. The Class 2 ores and or concentrates are those that contain the sulfide and other contaminants, such as copper, zinc, and so on. By placing a few grams of homogenized material into a small beaker or glass and adding a small amount of acid, a sulfur dioxide gas may evolve. The gas is a definitive indication of a sulfide ore. As for the calculations regarding sulfide ore, the Class 2 charge table will be used and will be presented in a future presentation. Placing a small amount of the ore sample or concentrate into another beaker and adding some nitric acid, a brownish colored gas may evolve. Once again, this is a good indication of a Class 2 ore. Note, however, the color of the residue or the solution. The bottom example shows the typical brownish color of the gas. The solution is turned green. This indicates that the ore is a Class 2 ore which contains a significant amount of copper. The reaction on the upper left. This example still shows the brownish colored gas. It is lighter in color, but so is the solution, which has turned to the same color as the gas. This is a reaction between pyrite and nitric acid. The contaminants are iron and sulfur. a typical Class II ore. The top right reaction is with sphalerite, where the gas still has a brownish tinge. Note the precipitate and solution color. It indicates that the ore contains zinc. The precipitate shown is zinc nitrate, which will become soluble if enough nitric is added to form the water required in the reaction in order to create a zinc nitrate solution. The nitric acid solution that was used to test the sulfide minerals, if any, produced that brownish colored gas, indicating that the ore had a sulfide complex in it. Do not discard. Let it stand and cool. Once cooled, dilute it with a slight excess of ammonia hydroxide to neutralize the solution. What may happen? A brown-colored precipitate may form. This is an indication of an iron complex. The precipitate will be ferric hydroxide, which in turn is actually iron 3 hydroxide. If your filtrate turns blue, the indication is that there is a presence of copper or nickel, and or both. If your precipitate turns white, your ore will contain zinc. Royal water. That is what it was once named. Today it's referred to as aqua regia. This powerful acid solution is 3 parts concentrated hydrochloric acid to 1 part concentrated nitric acid. Placing about 1 gram of ore into a beaker and adding 20 milliliters of aqua regia, heating it, and letting the material dissolve for about 20 minutes or so, then diluting with approximately 150 milliliters of distilled water. A white residue at the bottom of the beaker will likely be silica, that is, quartz. By weighing the percentage, may be calculated. If there are other residues associated that may be dark red-brown or black, these could be iron oxides such as magnetite or hematite. They may also be sphalerite or galena, which are sulfide complexes. After decanting, washing, filtering, and drying, the magnetite itself may be removed with a magnet confirming the mineral. In this example, those tiny white specks could be quartz. The brownish red specks may be hematite, and those dark specks could be magnetite or zincite. In a previous presentation, I discussed the ideal slag properties. I also talked about the color of the slag regarding the impurities that may be present. This slide is an addition to the slag color in reference to the impurities that may be present, or some of the unwanted metals in the ore or concentrates. Fire assaying is basically used for the pre-collection and the collection of the gold, silver, and platinum group metals. The calculations for the slag creation for the correct flux recipe are adjusted to mitigate any errors and or problems which are associated with certain metals or minerals, especially copper, nickel, zinc, selenium, and tellurium. The resulting slag will be either acidic or it will be basic. Copper will show up green or greenish in an acidic slag, and brick red if your slag is basic. Regardless of whether or not the slag is basic or acidic, cobalt is blue, manganese shows up as purple, iron, depending on the concentration, will either be yellowish in color to brown to even black. Antimony shows up as being greenish yellow, and the rest, well, cream white. Usually, excess amounts of flux constituent will be added to the charge to ensure that the charge is easily and readily fusible. At the same time, it must be strong enough to dissolve all the impurities so that they can be collected and fused in the slag. In most cases, the charge produced will give a satisfactory fusion even though the ore concentrate may have a varying amount of unwanted gangue material. A standard acidic charge can be calculated, which may be satisfactory for any ore that contains 60 to 100% silica. The flux must contain enough basic material to fuse all of the silica. Litharge and soda ash are used for this purpose. and the amount added should be reduced as the concentration of silica is found to be less, let's say 60%. Although the basic charge may be more than adequate, any ore that contains a lesser amount of gangue material will not need as much flux constituent, and therefore the quantities can be substantially reduced, saving money. The charge calculations are used to accurately calculate the charge constituents required. Analyzing the gangue material will greatly aid in the calculations if the gangue material and the concentrations were known. In this presentation, I discussed some of the additional methods of identifying the type of ore that you have, that is whether it is a Class 1, Class 2, or Class 3. I also discussed the importance of knowing the elements that may be complexed within the ore or concentrates. In the next presentation, soon to be published, I will be discussing the 9 steps associated in calculating those Class 2 ore types. These 9 steps have been combined and placed into what is known as the charge table and is used to calculate the required amount of flux material to be used to create the charge. These presentations are free to view, and if you have a YouTube downloader plugin, please be free to download a copy of these presentations for your own use, not to be given for profit. These are meant for education only, and I do not charge for these edited video presentations. If you like these presentations or benefit from them, or know someone who may benefit from them, please give them a thumbs up, a like, and a share. This would be my greatest reward. I thank you for watching. I am Rob Boyko, Boyko Mineral Exploration.